L by D stroke to bore ratio, that is also given by 1.2. So accordingly, you can find the dimensions. Then theoretical power of the compressor, if adiabatic efficiency is 85%, mechanical efficiency 90%. So whatever is your theoretical power, actual power comes out, you have to consider for both these efficiencies and find out the theoretical power requirement. And theoretical and actual COP. Fine. So theoretical COP is basically related to the Carnot part, that is 36 degrees Celsius and minus 10 degrees Celsius. And actual COP is what you get from the pH chart. The pH is more practical one. Okay. So this is what is asked. Is the information clear? Specific heat of the ice is given 1.94 because your MCP delta T, for that it is required. CP of water is a standard value. CP of ice is given. So 30 degrees water to 0 degrees water, then M into HFG, that is the latent part, and then again MCP delta T for the ice. So for that purposes, CP of ice is given. Any doubt to anyone for decoding the data?
No, sir.
Okay, so now open the ammonia chart. No, not chart, the table, sorry. It is to be solved by a table. So now refrigerating capacity, what is given to me? 10 tons per day. Correct? And that is like 24 hours per day. So I can get it in per hour basis. Correct? And then 10 tons. So convert it into kg also. You need to convert into kgs. And then finally 3600, that is to convert into seconds. So that you will get it in kilowatt. Otherwise, kilojoule per minute, kilojoule per hour, whatever unit comfortable with. So here the point to be noted is 4.1868 or 4.187, whatever, into delta T for 30, then 335 as the latent heat, and then 1.94 into 0 to minus 6. So none of these should be skipped. Is the calculation correct?
Yes, sir.
Okay, so 10 ton per day, 24 hours per day. Anyways, per day getting cancelled. So this is ton per hour converted to kg per second. So that will give me the m dot. And then corresponding CP delta T, that is sensible part, or HFG, that is latent part. Okay, so this is my refrigeration capacity or the load, whatever you call it. Now read the table. So if you start imagining the cycle, then your dry saturated enthalpy at minus 16. So we have selected Hg at minus 16. The chart is with you, correct? Ashray table.
Yes.
So read it. Then you are asked to calculate the volume also. So you may require Vg also afterwards. Then S2 equal to S1. And for that S1 is known, that is Sg at minus 16. So I know that. I can read it from the chart. And H3 equal to H4. It is a simple saturation. So that means it is liquid enthalpy. So that is HF3. So that's why HF at 36 degrees Celsius. Are the values correct? Table from the taken from the table.
Yes, sir.
Fine. So you know H1, you know S1, which is equal to S2. So accordingly, we can find out H2 also afterwards, once you get the temperature and all. And H3 equal to H4, which is HF3. Correct. So now I need to find the mass flow rate. So total Q dot I know, just now we have calculated, divided by the specific refrigeration effect, H1 minus H4. H1 is known, H4 is known, which is as same as HF3. Isenthalpic expansion. So I get the mass flow rate. Correct. What you have found out earlier is the mass, this one. is related to the ice part, not the refrigerant. Ammonia mass flow rate is not given. So that I have found out. 10 ton per day and 24 hours per day. This is related to the ice, not refrigerant. So how to find the refrigerant? So this is the same. Q dot is equal to M into delta H for the refrigerant. So whether you use the table or the chart or whatever, you can read the values of H1 and H4, which is related to the refrigeration effect or evaporator load, whatever you call it. And accordingly, you can find M dot. Is the calculation correct?
Yes, sir.
Fine. Now you got a dot. Second job is to find out the E superheater. So S2 equal to S1, where S1 is Sg at minus 16, a value which you know. Correct. Then Sg at 36. That means saturated. That you know. And you can find out that 5.84 is much larger than 0.19. Confirm being the superheated one. Correct. So S1 equal to S2, which is S2 dash saturated plus Cp into ln times of T2 by T2 dash. T sup by T sat. So to find out T superheated at temperature. Cross check the calculations. The value of Cp is also given in the table. Liquid specific heat and vapor specific heat. Ours is vapor. Correct? And that word saturated. That means 36. So that is why 3.405. Here, can you show this? See this?
Oh, yes, sir.
That is related to 36 degrees Celsius. So 3.405 यहाँ से आया. And ice के लिए 1.94 यहाँ पे दिया
वो
हुआ.
दिया था ना given.
So some information given in the table, some information given in the text. Use it wisely. Is the calculation correct?
Yes, sir. Yes, sir.
So now you can see that 36 degrees Celsius is the saturation value, and what we got as the superheated one is almost like 100 degrees Celsius. 373 K means 100 degrees. Correct? So 36 to 100 is your superheated part. Do you agree?
Yes, sir. Yes.
Okay, any doubt to anyone up to this part, whatever we have done? We found out the refrigeration effect by using ice, that same by using the refrigerant, that is ammonia, found out the m dot, then equating the entropy under the assumption of isentropic expansion, we found out the superheated temperature. So use this to find out the enthalpy. Correct? Now the cylinder dimensions. So cylinder dimension pi by 4 d square into L into N. Correct? Nothing as such given for double acting and all such kind of things. Which will be m dot into specific volume, that means the total volume, and the volumetric efficiency. So m dot you have calculated refrigerant, then specific volume, which you can read from the table, correct, that is corresponding to minus 16 degrees Celsius. And for the vapor part, so where is this specific volume? Yes, over here volume. So my this 0.52936, that is over here. Same as that of the steam table. Okay, m dot you have calculated V1 taken from the table as the saturated gas specific volume, saturated vapor. Volumetric efficiency given to you, that is equal to pi by 4 into d square into internal relation known, so 1.2d Then n, that is your speed, so 1200 rpm, convert per minute to whatever convenient, what is your unit for the m dot, kg per hour. So multiply by 60, kg per second hota to divide by 60. Fine. Is the calculation correct?
Yes, sir.
Okay. So observe that the diameter is 0.13 meter. How much it is? 130 mm, or basically 13 centimeter, correct?
Yes, sir.
So that is a somewhat logical thing, correct? I have observed in last 10 years, people solve this, but they miss with the unit and then they write down 0.13 millimeter. How will you manufacture it? Or otherwise 1.3 kilometers. Something like that. So at least cross check the units. That is the importance of assigning the unit. If I ask, say, evaporator load or condenser load, I think 4 years ago, one student has answered in the ESC question paper. The student has answered for the condenser load of nearly, well, rather, 1.5 megawatt. Is it a power plant? So please cross check the answers when you solve something. Pay true attention, at least, to the unit and defend that, okay, this is logical, acceptable one. The calculational mistake is something like completely on your side. But the logical mistake, that is something which you can always avoid. Okay. Now power consumption. So now you know temperature T2 and this is vapor form, superheated vapor rather. So Cp delta T is valid. Correct, you calculate H2. So the moment you get H2, you get the power M into H2 minus, or M dot, I should say, H2 minus H1, and there are the efficiencies given: diabatic efficiency and the mechanical efficiency. Are the calculations correct? Please cross check.
Yes, sir.
Right, so H2, if correct, then naturally P also would be correct. So around 15 kilowatt compressor power. Fine with this. Any doubt to anyone for this numerical? So now you can solve the numerical. If I give you the table, even if I don't give the table, you can refer to Asher table, find out the values, substitute. So this is the theoretical approach. One is the graphical approach. That is by using pH chart. I tried to take sample example. Fine. Should I move ahead?
Yes, sir.
Yes, sir.
Theoretical and actual COP. Theoretical COP, that is your enthalpy part. Actual COP is what you are given with respect to the uh, ice formation and all. The compressor load which I have calculated. Fine. Carnot COP will be with respect to that temperature only. Rather, those temperatures 36 and minus 16. Fine. Any doubt? Is the calculation correct?
Yes, sir.
Okay. Should I move ahead? Any doubt to anyone?
No, sir.
Okay. An ammonia refrigerating machine has working temperatures of 35 degrees Celsius in the condenser and minus 15 degrees Celsius in the evaporator. Assume two cases, dry compression, wet compression. You are going to repeat what you have learned in your laboratory part. Calculate for each theoretical piston displacement, theoretical power consumption and COP. सब कुछ सिखाया हुआ है लैब में, करो. Take the ammonia chart, draw the lines for 35 degrees Celsius, minus 15 degrees Celsius, draw the horizontal lines, complete the cycle for wet compression and dry compression. This is what exactly you have done in your laboratory session. Okay, Karande sir का कौन सा lecture है? Which was actually scheduled at 2 o'clock, that will be at 3 o'clock now. It's the internal
Yes, sir.
exchange. Yes, I have to go to the account section for some administrative work. I have to go means I am called at 3 o'clock over there to be present at 3 o'clock. That's why this adjustment. और क्या कल से आने के लिए बोला है क्या फॉर लैब सेशंस?
नहीं सर, हमें कुछ नहीं बोला सर.
तो छोड़ दो. व्हाई यू आर गोइंग टू आस्क फ्रॉम योर ओन साइड? नहीं बोला तो नहीं बोला.
हाँ सर.
I have taken the lab today. I don't want to get involved in all these issues. बुलाना है नहीं बुलाना है, कहीं से तो कर रहे हैं ना, करने दो ना, क्या प्रॉब्लम है?
फिर टी-वाइज को बुलाया था ऐसा वो लोग बोल रहे थे.
हाँ टीवा को बुलाया. यस, बैच वाइज. Yesterday there was a discussion about making the batches and all those things. ना तो मुझे बैच पता है आपका, बैच 1 टू बैच, एंड ना तो मुझे कोई इंटीमेशन है कि उनको बुलाओ. व्हाई आई शुड पुट यू इन सम ट्रबल? जहाँ पे हो सुखी रहो. नेक्स्ट वीक में देखेंगे.
हाँ सर, we'll see for official notice.
हाँ एग्जैक्टली. योर फाइनल ईयर क्लास कोऑर्डिनेटर Suryavanshi sir has to like pass something, right, as a piece of information, official one.
Yes sir, we'll wait for that.
It's surprising either to you or to us faculty members. ना आपको कुछ शेयर किया है ना हमें कुछ शेयर किया है, तो क्यों उस झंझट में पड़ने का? And how can they call for like such a short notice of 2 or 3 days? People may not be in Mumbai present.
So I guess they've given the hybrid mode option, so those who want to come can come, something like that.
Then why would anyone come?
So they are pretty eager to come as far as I know, the T-wise.
Hey, those who are staying in Mumbai, that is okay. But why would someone come all the way from some outstation part?
They might want to spend their college days. Actually enjoy them.
So then you should be somewhat nostalgic about it, right? This is your last sem. If you get some time to spend in the college, इसके बाद आप थोड़ी college देखोगे. You should be somewhat emotional, not T-wise. They can come in next year also. This is your last sem.
Yes, sir.
Surprising. Either they are having very keen affection towards studies, or you are emotionally retired. With that, 35 degree minus 15 degrees. Yes or no? Two lines.
What, sir?
Two lines corresponding to 35 degrees Celsius and minus 15 degrees Celsius on ammonia chart. Done or not?
So no, we don't have the printouts.
प्रिंट आउट्स की क्या जरूरत है? कंप्यूटर पे भी बना सकते हो. लैपटॉप मोबाइल में नहीं होगा. आई एग्री. बट यू आर अवेयर कि हमें ऐसे एग्जांपल सॉल्व करने. नो नीड टू हैव प्रिंट आउट. लैपटॉप पे यू कैन यूज पेंट और व्हाटएवर इट इज एंड ड्रॉ द लाइंस. More you make the practice, easier for you to solve such kind of numericals in MST and ESC.
Yes, I will check.
So has anyone drawn using the laptop itself?
So how do we interpolate between the temperature line?
Huh? Means what? Vertical lines, horizontal interception, linear interpolation. 35 means between 20 and 40. 20 degrees temperature vertical line, 40 degrees temperature vertical line. Linear distance, horizontal distance. You want 35. 5 out of 20 is 1/4. So 1/4 of distance away from
But
40 degrees Celsius.
is it linear only? Because the distance between 100 and 120 and the distance between 0 and 20 is not the same, right?
Temperature line? Temperature lines are linear one. Since your slope is changing for that saturated liquid line, the distance is different. But if you observe two temperature lines, they are always parallel. Done. This is what I got. Cross check.
This is something like that.
समथिंग दॅट नाही बाबा चालत. लॅबमध्ये दांड्या उडतात तसं होईल.
नाही सर ते स्क्रीनवर कसं बनवणार ते फक्त बघितलं रफली असतंय ते.
Why you have any software not to draw the lines? Those are using saying not for mobile. They can draw horizontal lines. Rather on graph you cannot zoom. On laptop you can zoom and find out the exact distance. That is what I did. Find the diagram.
Yes, sir.
Okay. So 2 lectures before this one, pointed out minus enthalpy, negative enthalpy. Nothing wrong in that. It is measured with reference to some particular reference substance, reference state, whatever you call it. So as such, it is negative. What we are interested in is the enthalpy difference, and that has to come positive. So minus 600 doesn't mean as such. It's not the absolute value. Ultimately, it's a relative one. Fine. So you can read the temperature also, T2 directly from the chart. So need not go for the superheated part calculation using the thermodynamic equations. So you can read T2, then H1, H2, and H3 equal to H4, isenthalpic expansion. And volume, specific volume you require because your further calculation may be related to the compressor part. The density is known, reciprocal of that. Fine, this is my dry compression cycle. So refrigeration effect, H1 minus H4. Both values known to you. Power consumption, compressor. So H2 minus H1, both values known to you. Then mass flow rate. Now the refrigeration effect is known. You substitute in any of the units. I have taken 211, that is kJ per minute. You can use 3.5167, that is kJ per second. Or 12,660, that is kJ per hour. So based on that, your mass flow rate will be kg per minute, kg per second, kg per hour. And that is corresponding to 1 TR. So this is per TR. Correct? Then theoretical piston displacement, that is m dot into V. So your m dot itself is per TR. So multiply by the specific volume. You get the volume flow rate also per TR. Correct? Is it 1 ton of refrigeration corresponds to 211 kg per minute. So this is per TR, your mass flow rate per TR. If you substitute over here, what you get the volume flow rate is also per TR. Then power consumption per ton. And the COP. So 4.056, the answer which I have got for the dry one. Now let us go to the wet. So this is the wet cycle. And here you can see this is the dome. saturated liquid and saturated vapor. Here, fortunately, you can observe this very clearly. So here it starts at the wet part, following the line, it comes dry saturated at the exit. Whereas in the earlier chart, your entry itself is dry saturated. This is your saturation curve. Correct? Slope is totally different. So dry saturated at the entry itself, the exit would be naturally superheated. So your refrigeration effect is drastically changed. Now let us see compressor work. Use cross check.
Yes, sir.
Fine. So now you know about the H1, H2, H3 and H4. So repeat the same set of calculations. Refrigeration effect. H1 minus H4. Power consumption, that is compressors. H2 minus H1. Mass flow rate. And here you can see that it is drastically reduced. Earlier it was 0.196. ये reduce नहीं, ये कम होगा ना, increase, correct. Mass flow rate will be increased because your refrigeration effect is reduced. And that displacement also is increased, and power consumption also. And if the power consumption is increased, COP has to reduce. So our earlier case 4.056 COP. Now it is 0.6 directly. Why I have dry compression? This is wet compression. This is typing mistake. This is wet part. Fine. Any doubt? This is what exactly you have done for a lab course. Am I right?
Yes, sir.
So in theory lecture also we have repeated the thing. You have implemented successfully the same thing in your lab. Should I move ahead?
Yes, sir.
Okay. Now comparison of the Carnot cycle with the VCC. So isentropic compression is same. Correct? Then isothermal heat rejection. As far as the phase change is concerned, we can say that okay, that is also the same thing. Superheated to saturated is the extra part. So that is why it is shown over here as the extra part. Correct? Otherwise, isentropic compression same. Then isentropic expansion. Instead of that, what we have got is the isenthalpic expansion. And since it is a irreversible process, so there will be the slope slightly towards the right hand side. Correct? And because your S4 will be greater than S3, so naturally right hand side, irreversibly. And the again isothermal heat absorption, that also we try to keep it as possible, as constant temperature as possible, as isothermal as possible. So there is a problematic for the compressor outlet, that is a superheated one. So if you go for the heat rejection, it no more remains as the isothermal one. Once it enters into the dome, inside the dome, it is isothermal one. Correct? So the Carnot cycle basic deviation over here, because of the sensible heat part, so no constant temperature. Then the nature of the expansion, in the Carnot it is isentropic, here it is isenthalpic. Enthalpy remains same, so naturally entropy has to increase. Correct? And accordingly there will be extra part for this. ये क्या है बाद में बताता हूँ. This is one extra part, this is one extra part. Do you agree?
Yes, sir.
So let us discuss about it. What is my assumption, or what are my assumptions? That is, state 1 and state 3 are common for both the cycles. So if you construct the VCC, let's say 1, 2, 3, and 4, that means this 1, 2, 2 dash, 3, 4. And if you construct the Carnot cycle, then it would be 1, 2 double dash, 3, 4 dash, 1. So my sun is also the common for both the cycles. State 3 also common for both cycles. State 2 differs here and here. State 4 differs here and here. Do you agree?
Yes, sir.
Fine. So under these assumptions, we will try to analyze it. So there are two irreversibilities. One, over here, non-isothermal heat rejection. Correct? So irreversibility due to non-isothermal heat rejections, that means entire process 2 to 3 now getting split as 2 to 2 dash, which is the sensible part, and 2 dash to 3 is the latent one. Correct? And the second part is the irreversibility due to the isenthalpic throttling. In Carnot cycle, what we assume is an isentropic expansion. Here it is isenthalpic throttling. So process 3 to 4, which is slightly different than 3 to 4 dash, which would have been the isentropic one. Correct?
Yes, sir.
Yes or no? So now let us try to analyze it. So I will say this extra part is the additional work required due to the superheated section. Let's say my compression starts from here. If somehow I end the compression at this point, and somehow I keep a restriction as this to be the isothermal heat rejection, and resemble it very close to the Carnot cycle. Do you agree?
Yes.
Correct. So that is not our case. So this A1 is that additional work required. Now who will do that work? Composer only. And then this A2, the loss in the cooling effect, if you would have executed an isentropic expansion, this would have reached at point 4, and the heat absorbed would be 1 and 4, H1 minus H4. 4 means what is it? 4 dash. But because of the isenthalpic expansion, it finally ended up at this point, and as such, the refrigeration effect is reduced for this 4 to 4 dash. Baki 1 to 4 is common. Are you getting it?
Oh, yes, sir.
Okay, so A1 is the extra part in the denominator, that is compressor work. And 2 is the loss in the numerator, refrigeration effect. So your COP is bound to reduce. Correct? In the numerator there is a loss, in the denominator there is increase. Cumulative effect is further loss. So as such, COP of the actual practical cycle will be much lesser than that of the theoretical one. Theoretical in this Carnot one, corresponding Carnot one. Am I right? Any problem to anyone?
No, sir.
Now I introduce this opposite area to that of A2 as A3, and I will say that it is the additional work required. Why this is required? As no work is recovered during expansion. Ours is isenthalpic expansion. Joule's porous plug experiment. If you use the turbine, there will be the work generated and you can supply it to the compressor so that your compressor work requirement could be reduced. But if you use a simple capillary or a thermostatic expansion valve, you cannot harness any kind of work from that. Correct? So even though the energy is having that potential to harness it or get some work out of it, harness the work, but still we are not doing it. Correct? So that is a loss of the available energy. So because of that, the third area, A3, is considered over here. Any doubt?
No, sir, no doubt.
Okay, so there we require that additional work because you're not gaining anything out of it. Now, if you consider the Carnot cycle, that is 1, 2 double dash, 3, 4 dash, and 1. Correct? So this is my area E, that is over here. E1, then 4 dash, C, and E. Correct? Yes or no?
Oh, yes, sir.
Okay. Then the vapor compression cycle, over there it is 1, 2, 2 dash, 3, 4, and 1. Correct? So that would be the area as E1, 4, sorry, here 4, D, and E. So what is the loss here and here? So naturally this area. Correct?
Yes, sir.
Fine. So my refrigeration effect is reduced. Correct? This much is the loss. So that is reduced. So naturally my COP has to reduce. It will never be as the same as that of the Carnot cycle. Now the Q absorbed in the Carnot cycle minus Q absorbed in the VCC. So how much is that? The hatch part, correct? D4 4-CD. Correct? We have seen earlier
Yes.
part is this, new part is this. So hash part is the balance. And that will give me either H3 minus H4 dash is as same as H4 minus H4 dash. Because H3 is H4. Same. Right? So that is what my area A2. Correct? H4 and H4 dash. H4 is greater, obviously, than H4 dash.
Yes.
Correct? So Carnot heat interaction minus VCC heat interaction will be a positive value. I hope you agree.
Yes,
Yes,
sir.
sir.
So this is called as the throttling loss. That is your area A2. Correct? Now you consider the Carnot cycle. So over here I get area as E, then 2 double dash, then 3, then C, and then E. Agree? A simple rectangle.
Yes.
Now what about the vapor compression cycle? It would be E, then 2, then 2 dash 3, right? Then C, and then E. Area under the curve. Right?
Yes.
2, 2 dash 3, C, E. So now I can see that the work input is increased. Correct? So naturally again COP has reduced.
Sir,
Yes.
increased
Yes.
from 2 double dash to 2.
Huh?
2 double dash to 2 मध्ये वाढलं ना.
I'm showing the cycle. So that is E2 2 double dash 3 CE. Me 2 double dash दिलेलं नाही एवढंच. It has to follow the same constant pressure line. Na? Why pressure would change? Temperature would change, pressure remains constant. So E2 3 CE in bracket E2 2 double dash then 3 CE. Now my work input is increased. So that is why COP has to reduce. Correct? Agree?
Yes.
Okay. Now Q rejected in the Carnot cycle and Q rejected in the VCC cycle. What is that area? Only this much difference. Carnot cycle is this. VCC cycle is this. So how much is the difference? 2 dash, 2 double dash, 2, 2 dash. So this is a triangular part. Do you agree? Heat rejected is condenser.
Yes.
So this part is called, area A1 is called as the superheat horn. Since it is a triangular part, we call it as horn. And since it is in the superheated zone, we call it as superheat horn. Fine. Any doubt or not?
No, sir.
Okay. Now we would like to discuss about A2. And I will say for the Carnot cycle, that means 1, 2 double dash, 3, 4 dash, and 1. Then what is the network in the Carnot cycle? That is rejected minus absorbed. Correct? So as such it would be, instead of E starting with E, now it would be the difference. So it is 1, 2 double dash, 3, 4 dash, 1. Do you agree?
Yes, sir.
Fine. Similarly, try to get the network for the VCC. Now in the VCC you will observe it is 1, 2, then 3, okay, then 4 dash, then C, D, 4, 1. Correct? ये extra part है, means you have to do that work, compressor side, and this is the loss in the refrigeration. Do you agree?
Yes, sir.
Fine. So now you got both the areas, and now you will substitute these as W net Carnot and W net VCC in the same formula. That means your area A1 superheat horn is extra part, and area A2, which is the loss in the refrigeration effect. That also you need to consider. Fine or not? Any problem to anyone?
No, sir, no problem.
Otherwise, you can ask the doubt. Correct? And now I will say that Q absorbed for the VCC is Q absorbed for the Carnot minus that A2 part. Q absorbed is your evaporator. So over the VCC that means 4 to 1. Over the Carnot cycle it is 4 dash to 1. So what is the difference? Area A2. This. Correct? Are you getting this?
Yes.
So now you substitute W's, you know, Q's, correct? W here you can substitute. For the VCC that is equal to the total pura mila ke is equal to the Carnot work plus area A1 and plus area A2. This is also lost because it is the extra work for the compressor to be done. This is also loss because this is the refrigeration effect which cannot harness. So both are losses only. So both are positive sign. Plus area A1 and plus area A2. Do you agree?
Yes, sir.
So now you substitute COP or VCC. So this is Q evaporator of the VCC cycle divided by net work for the VCC cycle. So here you can observe that Q absolute for, well, Q absorbed in the Carnot and here it is W net in the Carnot cycle. What I'm interested in is this area part. Something which is more like a rigid part, stringent. We cannot play with it as we want. Correct? So COP in terms of the COP Carnot cycle also Q absorbed means what? Q evaporator only, no? Q absorbed is as same as Q evaporator. So let's say Q evaporator for the cycle minus area A2. And this is W net for Carnot, W net for VCC. So main part is this area, out of which you can observe that for the numerator it is the minus part and in the denominator both are plus part. So your COP of VCC is bound to be lesser than the corresponding Carnot. Correct? Numerator reducing so that it will come down and denominator increasing so that again COP will come. Do you agree?
Yes, sir.
Now more concerned toward this. ये कुछ तो हैच करके रख. What is this? Let's see. Okay. So we define for the cycle efficiency. This is the only definition thermodynamics as far as refrigeration is concerned. The efficiency is a function of COP. So the COP of the VCC divided by COP of the Carnot cycle. The COP of VCC you have just expressed in terms of the Carnot cycle. Correct? So here it is Q by W and here also Q by W. So here you can see that it is 1 minus something, in the denominator it is 1 plus something. So here it is bound to reduce, here it is bound to increase. So overall effect, this will be further lower. Agreed?
Yes, sir.
So this is called as the second law efficiency. Even though you are measuring the performance in terms of a COP for the refrigeration cycle, still you can express the relative part as the efficiency only. Because we have proved that COP of the VCC will be always lesser than that of the corresponding Carnot cycle. So as such, that is something which we call it as a relative efficiency. The actual thermodynamic word is the second law efficiency. Fine. Any doubt to anyone?
No, sir, no doubt.
Good. So this is a good indicator to understand, to analyze the deviation of the standard VCC cycle. What is the meaning of standard? Here it is start at dry saturated vapor compression and start at saturated liquid expansion. That is what is standard VCC, correct? And Carnot cycle. So my job as a good engineer, RAC engineer, HVAC engineer, whatever you call, is this relative efficiency or second law efficiency has to be as close as possible to 1. That means indirectly my VCC cycle, vapor compression refrigeration cycle, will be as close as possible to that of a corresponding Carnot. So we proved Carnot is the highest, VCC will be lower. Take the ratio, keep the controlled, what I can say, processes in such a way that your areas A1, A2 would be the minimum one. You can observe over here, if area A2 is 0 in the numerator, what would happen? There is no area A2. So this becomes 1, correct? 1 minus 0 upon whatever, doesn't matter. So here. And here also, area A2 is close to 0. Area A1 also close to 0. What will happen? इसको क्या फर्क पड़ता है? So 1 minus 0 upon 1 plus 0. क्या फर्क पड़ता है? So 1 upon 1. So we have to keep this area A2, which is the loss in refrigeration effect, and area A1, which is the extra part for the compressor work, to be as least as possible. Do you agree?
Yes, sir.
Fine. Good. Now, बचा ये एरिया, इसको देखते हैं क्या है. So my assumption, the first assumption is change in K and P negligible. छोड़ दो. Okay, because our system is not moving, our system is not falling down or anything. Correct? टाइम काय झाला रे बाबा? हे संपेल का?
3 वाजले सर 3.
हा मग ठीक आहे, मला जायचंय तिकडे. चला चला, हे नेक्स्ट टाइम.
Okay,
Any
sir.
doubt up to this part?
No, sir.
Yes, sir.
Good.
Bye, sir.